Hello everyone, I am trying to get your MATLAB slides done for tonight. Sorry, I'm a little bit later than usual. Let me go ahead and share my screen with you. This is our last lecture before the end of the class, the end of the semester. And so tonight we will be talking about our last topic, which is loop statements and vectorizing code. So here are the slides. The slides are up on Moodle, so you can go ahead and follow along with those. And this is displaying backwards. So let's swap. Ta-da! All right. So just to finish off the course, to review what we need to do, we'll be having the take-home exam, which I will post for you for next Monday. You can expect to have a couple of questions to work on, and you'll have until Wednesday to finish those. Also, the following week, we'll have our final project workshop, which will give you an opportunity to discuss with me any questions or problems you might be having with your final project. And that will be due on Wednesday, May 13th at 10 p.m. All right, so what we're going to discuss today are the for loops, nested for loops, while loops, loops with vectorizing in matrices, how to do vectorizing of codes, which is a topic we touched on earlier, and an interesting topic of timing, how to tell how long your code takes to run. So let's get through the for loop. So just to give you an overview of loops, there are a couple of different kinds of loops. Generally, they're considered to be counted loops and conditional loops. So counted loops is when you know how many specific times you need to go through a loop. That doesn't mean it can't be a variable. A variable is fine, but it would be some specific number of times that could be saved in a variable or a particular actual numeric number of times. And in a conditional loop, that's when the loop is going to iterate when you have some condition that needs to be met. So a for loop follows this basic setup. You're going to have a for statement, and then you're going to have some iterator or index I, and then you're going to have that equal to some range. So in this case, it's going to run from the range of 1 up to 5 inclusive. And you see what I've done here is set this up to print basically just the number I, its index as it's going over the loop. And when we run this, we will see that it runs up 1 to 5. So you see that this illustrates how we have a known number of times that it's going to run, which are explicitly mentioned here, with the index running from 1 specifically up to 5. And this is going to contain the iterator variable, which we pointed out is this I right here. And you see that here inside of this, we're actually printing the I. So one thing to notice is that the iterator does not necessarily have to appear in the code. So here's an example of another loop that has something that doesn't have any, oh, it looks like I cut off the for, sorry about that. But that doesn't necessarily have any I in the code at all, and that's fine. You don't necessarily need to have it in there. It's only just to keep track of how many times you've gone through the loop. So what are loops good for? There's actually a number of things that loops can be used for. So one of them is to get input from a loop. So this is an example from your book, which is going to take input from a user. So what we might want to do is we might want to collect a specific number of entries from a user. So for example, here we're going to have a for loop that's going to have some iterator here that's going to collect 3 inputs. So this will take 3 numbers. Here we have the input statement and some text to describe that, and then that will be returned into the input number, and then it's going to just echo that back. This is called echo printing, which means it prints back what the user typed. This is a simple example of collecting input. So if we run this, then this is what it's going to look like. The user typed 3, 4, and 5, and because of the formatting here, it's going to be printed out in the decimal version. This is echo printing because here the input is an integer, and it basically just prints back what it is they typed in right there. We can also use this to calculate running totals. This brings us to the idea of idioms. So an idiom is like a pattern for the way things are typically done. So if you have a way that you typically do a task, you might have a sort of like a template code for how it is that you do this. So actually, a lot of these things that we're talking about with how loops could be used could be considered to be idioms. So a common use of loops is to iteratively calculate the sum or product of something, a running total. So each time you go through the loop, you could add or multiply the current entry, subtract, divide. Other alternatives, of course, do exist. And then we would want to print out the total at the end. So for example, here is a sample program that's going to sum some numbers. So here we're going to have a random number generator generating an integer from 1 to 3 inclusive and storing that into n. And we start by having our running total being initialized to 0. So an initialization means setting it equal to some value before the loop starts. Here we're going to have I running from 1 up to n. So this means the number of random numbers, the number of inputs that we'll take is going to be random on from 1 to 3. And so here we're going to actually get the number that's going to be input. So the number of numbers is random, but the number that's entered is typed by the user. And so then what we're going to do is we're going to do the running sum by adding the current value of the running sum to whatever they input. So you see if they add in, say, 1, 2, 3, what it's going to do is it's going to add those up. So the running sum starts off to 0, and then 1 is added to that. So the running sum is now 1. And we add 2 to the running sum, so it's now 3. And then we add 3 to it. So that works out to be 6. Okay, so another topic we want to talk about is pre-allocation. And so the idea about pre-allocation is when you're going to have a vector, if you don't know how big it will be, then you can't really pre-allocate because you don't know how many spaces you'll need. But if you did know how many you're going to need, like how many numbers, how many inputs you're going to have, what you could do is you could either start your vector out being empty and grow in spaces for each of the data points that you need to put in, or you could set up a vector and have basically placeholders for each item that you're going to need to put in. Now, which way do you think is going to be more efficient? Well, each time you need to go and look for some memory space, you have to go and you have to find some location on the disk that has the memory that you need. So that's really not the best way to do it, because then you would have to do that multiple times if you did it every time you need to expand the vector. So a better way to do it perhaps would be to say, oh, well, I know I need 5 places. Okay, let me just go look for a place on the disk that has 5 places to store the number, enough memory space available, enough bits available to store my whole vector, and reserve that, and then I'll just fill them in as I go. So as it turns out, that's a better way to do this. So that's the idea. And the reason why we're talking about it here is because we might use a loop to fill a vector. That would be a very good use of looping. So inefficient is to search for memory place for each entry, as we just mentioned, but an efficient way to do it would be to search for enough memory to hold the entire vector and then fill the vector over the loop. So you can see here that this is going to illustrate how that would work. So here again, we have a similar thing. We're going to pull in a random integer on the range of 2 to 5, and so the n will hold that random integer, which is going to be the size of the vector. And so what we're doing here is this is our pre-allocation. This is we're assigning all the zeros in the vector from places 1 to n. So you see, we don't necessarily need to know the value of n before we run the code. So n could be anything between 2 and 5, but for a particular iteration of running this code, n will get assigned one of these numbers. So at the point we get to this line right here, we'll know what n is equal to. So we can then allocate a vector, numvec, to have zeros in all of those positions. Now what we're going to do here is we're going to run through this loop here, and we're going to fill the vector. So this is going to collect the numbers from the user, and so it's going to have however many it decided from the random number generator. That's how many positions in the vector there'll be. So we know we already have a position for each one, and here is where we actually get the number from the user. And then the I is going to be the index to point to the position in the vector where that number is going to go. Notice that the I is the same I as this index here. So it's really key to understand that in the vector, we're using this I to point to the position where we're going to place the number that the user has just input. Then what we're going to do is at the end, we're going to print the vector, and this is a formatted. Okay, so here we go. We're going to enter some numbers, right? So in this case, it was 5 was selected, and these are the numbers the user typed. And so we see that those are placed into the vector because we're displaying the numVec right here, and there it is displayed right here. So we can also use for loops with plotting. So this is illustrating making these sine graphs over here with different densities of number of points. So this one on the right is more dense with points than the one on the left. So this is 20 points and this is 10 points. So let's take a look at how we could do that. So it's a good idea to call to mind how it is we can do the plotting. So we had plotting in a few chapters back. So what this is going to do is this is going to create some subplots. You see that we have 2 graphs, 2 sets of axes inside the same window. So that's what this subplotting is doing. And so what we're going to do is we're going to run over I from 1 to 2. So this means we're going to have 2 subplots. That's the range of our for loop. So here what we're going to, and recall this is dividing up the space in the window. So it's saying it's going to be a 1 by 2 space on there. So there are 2 side by side. 2 by 1 would cause one to be on the top and 1 to be on the bottom. So remember that linear space is a function that's going to divide up a certain range in a linear way. So this is going to run between 0 and 2 pi, which makes sense for doing a sine graph. And then what we're doing here is we're multiplying the 20 times I, which is our iterator here. So it will start off being 20 times 1, so 20. So this is telling us how many points we're going to have, and the lin space will then linearly space them over the 0 to 2 pi interval. Here we have y equals sine of x, and so that's going to give us the y values that correspond to the x values that are here. And now you see what we're going to do is we're going to declare our subplot right here. Okay, so here we decided we're going to iterate over 2, so this needs to match what you put here, or else you won't fill all the plots or have too many. So they need to match. And so this is the line that specifically uses the subplot command, which is going to break the window into the 1 by 2 plots. And then it's going to select the ith plot. So the first time through, it will select the first plot, and the second time through, it will select the second plot. So here we're going to plot the x and y values as they're set up here. So this will have a density of 10, so there'll also be 10 corresponding y values. And then this is formatting the way that this is going to be shown. So it's going to be the open circles is what this is telling us, and it's going to be in color black. And we're also labeling the x and y axes in the title. So those are showing up. Here's the x-axis and the y-axis labels, and this is our title up here. We could have, of course, put some variables in here as well, and that could have changed the titles to reflect which one it was plotting. So for loops, why only have one when you could have more? What you can do is you can have nested loops, and that means you might have an outer loop and an inner loop. There's no particular limit to the number of nesting that you can do. However, the nesting is typically done, usually you don't do too many nested. We'll talk about it being nested one inside the other, and then I think it'll just transfer to having things be further nested if you have need to do that. So this is what we're doing here. The syntax is going to be for a loop variable equals range. So this is basically what we've seen. But since there's an outer for loop and an inner for loop, we'll need to be sure to have independent variables for each of these, and each of them can have a different range. This is the outer loop, which is the one that happens first, and this is the inner loop, which happens down in here. So as we go through the loop, is what's going to happen is this is going to start at a particular value, say like 1, okay, and then this inner loop is going to then take on its value. So it might go, 1, and then this one is going to update first to 2, 3, 4. So your combination is going to be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Let's say you're going up to 5 on this. Then this one is going to update to its next one. So then it'll go 2, and then this is going to go over its range all over again, starting with 1, 2, 3 all over again. And don't forget to put your ends to stop your loops. So let's actually just take a look at that. This is an example where I've actually done just what I was describing here. So we have an outer for loop where I is running over the range of 1 to 3 and j is running from 10 to 12, just to make this interesting. And all this is going to do is it's just going to print the I and j values. So when we take a look at this, what we see over here is that the I is staying the same for the outer loop and the j is cycling through all of its values. Then after j finishes, right, then the flow goes back out to the outer loop. And so now I will take on its second value, which is 2, and then j is going to cycle over all of its values, and so on and so forth until all of the combinations have been done. So this is really useful if you need to do something combinatorically, like say you have 2 things and you need to enumerate all possible things that could happen. This is an excellent choice for how to do that. So here's an example to use a double loop like that, nested loops, to do multiplication tables. So what we're going to be doing here is basically we're going to write a function. It's called out matrix, which is going to, the out matrix is the thing that gets output, and this is going to be multiplication table, which is the name of the function, and the input to this is rows and columns. So let's just recall that this is the format that we learned back when we learned how to define functions earlier in the semester. So here it's going to just describe what's happening here. Right? It's going to basically create your multiplication table, and it's going to have all of the factors in there that you're going to see. Look here that we are using the pre-allocation that we talked about. So here is our output matrix, and it's being filled up with zeros with enough for the rows and columns, which is the input that will be telling the size of the output matrix. So here what we're going to do is we're going to run over I for the rows. So notice that the I will be completing all of, it will go I, and then each of the J's is going to cycle over. Oh, we have our honorary TA Max stop by. And we're going to cycle over J to get all of the different values of J here. And so then when that happens, we get our multiplication table, which we see is written down here. Here's our ones table, our twos table, 3, 4, and 5 tables being written out. We can also write a wrapper to run the script. And so here we have a wrapper script that is going to cycle over this to do your rows and columns. And so basically what this is going to do is solicit the input for the number of rows and columns, which is the input required for this. And then we're going to have our multiplication matrix table right down here. This is actually calling our function and running that. So this is a sample execution of that. Recall that when we use type to read in an output matrix, that it's going to report it back in scientific notation, which is what we're seeing here. So we also have other kinds of loops. We also have the while loop. So in a while loop, we can use this as a conditional loop. You use it when you don't know how many times the action will take place before you get started. It will execute as long as the condition is true. Note that some action must cause the condition to become false. Otherwise, your loop is going to continue infinitely, which is probably not what you want it to do. This is the syntax we have. We have while and then the condition. So we'll be using a statement here, true, false. And then we have whatever it is you want to do in your while loop. And then it will end when this condition becomes false, which suggests that there'll be some variable up here that will change value in the body of the loop. Just a few more words on infinite loops. In computer programming, an infinite loop or endless loop is a sequence of instructions that, as written, will continue endlessly unless an external intervention occurs. That is Wikipedia's definition. So usually we don't really want to have an infinite loop, so we should avoid those. All right, so example, this is a function using a while loop. It's going to check if the factorial is greater than the input number high and return the first number that satisfies that condition. So this is from your readings. This is the function definition, and you can see this is going to be called greater than high, and so the user is going to input some number, and then what we're going to do is we're going to generate the factorials until that number is going, the factorial of that number is going to be higher than high. So the first number that exceeds high will be the one that gets returned back, and this is a description of that, and this is our format. So here's I equals 0. Our factorial is going to start with 1. So while the factorial is less than or equal to high, we're going to keep continuing. And so what this suggests is that the value of factorial is going to be changing throughout the loop, which we see it does right here. And this is basically increasing the I by 1. And here you see that we're computing the factorial. And this loops through, and then this is the end of the while loop. And so eventually this will exceed the value of high. And so when that happens, then this will report back the greatest factorial. So we recall that this is the output value specified here. So here is our variable fact greatest, which is going to have the value of the factorial. And so that's what will be reported. But why stop there? We can have branch guards that are more complicated than that. So you don't necessarily just have to have just a plain statement that's true or false. You can have compound statements. So for example, something you might want to do is consider while x is greater than 0 and while x is less than 100, which would then give you a range of values, right? The range from 0 to, so 1 to 99 would all make the statement true. And so that's how you could look at a range. Make sure you'll have something that will increment your variable if you did something like that. You might also want to do an or statement, where you have x is less than 50 or y is less than 100. Either one of those could be used. So there's, of course, a whole variety of different logical statements you could bring together, but the typical kinds of things you'd want to do is link them up with and or to make a logical statement. So we can also use loops with vectors and matrices, and we can also vectorize. So what we can see here is what we can read data from a file and do some plotting with this. So what this is going to do is it's going to read data from a file, but it's only going to plot the numbers up to a flag of -99. So this is actually really interesting because it also illustrates this idea of a sentinel, which is a divider between the data sets. What this allows you to do is to have some data like we have down here and to pick up all the data up to when we hit this value right here, and then it's going to stop collecting the data. So this is going to do reading while the experiment D values are going to be before we hit this sentinel. It will be adding these into the new vector. And so this is a way that we can sort the data so that we can pick out only specific values. So this was in fact the input data, and notice that only 3 of them got plotted. And that's because we have 1, 2, 3, we have 4 values here. Oh, yep, there are in fact 4 points on this graph. So we would get 4 data points that would get plotted because we said while this is prior to the point of demarcation in the data that we are going to use. However, we could also use an alternate approach that's going to work a little bit better, and that's to use find. So here, instead of using that loop and the sentinel, we can use this find command. And what this is going to do is it's going to find where the value is equal to -99. And then that will be stored in here. This will return the position. And so then what you can do is you can go and pull out the data from 1 up to the point where you had mentioned that you had the point of demarcation. And then we can plot our graph, and we would get the same graph by doing this approach. We can also use a loop to collect input. So here's an example of doing that. So here we're going to ask the user to give a positive number or a negative number to exit. So you can see that we would be typing something, and so while the input number is greater than 0, so you see this right here is how we're going to tell. So if they enter a negative number, what's going to happen is this will become false, and so the loop will become false, and so it will end the loop, and it will say right, and that will be that. This is a sample execution of that. So here it's taking some numbers and it's reporting back, echo printing. So they entered 3 and 5, and then once they typed -6, that caused the gate to become false, and so the loop exited and typed by. We can also use counters with while loops. So even though we likely do not know how many times the loop will run beforehand, oftentimes what we want to know is how many times it actually did run. So we could use that to keep track. So we'd set a counter for that. So a counter is like a number here. You would set outside, and then what you're going to do is you add 1 to it each time you go through the loop. So if you started at 0 and you add 1 each time you go through the loop, the final value of the counter will tell you how many times you went through the loop. We can also use inputs with while. We can also use while loops to do verification of user input. So this is an example of how that could be done. So here we're getting an input number using the input function, and the user is supposed to enter a positive number. So while the input number is less than 0, what should happen is, well, we ask them for a positive number, right? So this will become false, and so what's going to happen is it's going to ask them to enter it again, and notice that this is going to overwrite this variable right here. So hopefully they will figure it out and now type a positive number. But you know, not everybody's all that bright, and every time they keep entering a negative number, this loop will continue to ask them to please enter the positive number. And that's how this can be used to verify the user's input until they figure it out and type what it is that they are supposed to input. And then after that happens, the loop exits and it gives this little message, encouraging message to them. Okay, here we can also use error checking in a similar way, but this time what we're checking for an integer. So we're going to have input number equals the input, and here we have some number is going to be, we're checking to see if it's in 32, this format. And so while this isn't happening, it's going to give an error message and continue until they type in the correct format. So what will happen is until the user enters an integer, it is going to continue to prompt the user to make some input. Oops, sorry about that interruption. Let's go back to sharing the screen. So this is more checking of input. So as we were saying, we can use this script in order to check whether or not a number is going to be an integer or not. Next slide. This is cool. Okay. And next, we're going to talk about vectorizing code. So we did talk a little bit about code vectorization way back when we were talking about doing the multiplication. And so we were talking about how you can loop over a vector, or how MATLAB automatically has that multiplication over the entire vector or matrix built in. So that built-in functionality of, say, being able to multiply everything through by 3 is what vectorization is all about. It's that automatic looping. So in many programming languages, the only way to iterate over vectors and matrices is to use a loop and explicitly loop over them. However, in MATLAB, that's not the case because it has that built-in vectorization. It's called a built-in iterator, which is going to automatically perform the looping over the vectors and matrices. So for example, recall v equals v times 3. That's going to be multiplying the vector, and it will iterate over the entire vector and multiply each element by 3 without having to explicitly write that out. So this is an example of comparing looping versus vectorized code. So here is an example where we're going to have an iterator I, and it's going to be explicitly running from 1 to the length of the vector. And so here we're going to multiply each element I times 3. And so when we do this, then we can get each item being multiplied out. In comparison, this is how the vectorized code would work. So in order to do a better job with this, we can write code using the built-in functions, because this will make our information be better. It will make our code run faster. Some of the things we have is the sum and product. We can use these to find the sum and product of every element in a vector or column in a matrix. We have cumulative sum and cumulative product, which do similar things. Min and max, which are going to iterate over and find the minimum and maximum values. Any, all, and find are also going to work with logical expressions. And we have our is functions, which we met, I think it was last week, which is letter is equal, that are going to return their logical values. That brings us to our final topic of timing. And so with timing, what this allows us to do is it allows us to actually find out how much time it actually takes for something to run. So what this can be used for is to time how long a code is going to run. And this can be important because what we can do is then find out how long it took to loop over something. It can be used to, important to make code more efficient, especially if it will iterate many times. This becomes important when we have large data sets in particular. Small savings can add up to make a program even faster. We use vectorized code to improve its runtime. The tick-tock functions are used as a pair, and those are going to determine how long it takes for code to execute. So here's an example of using the tick-tock function pair. We put place tick at the beginning of the code you want to time, and you place talk at the end, and then it will automatically report the time elapsed. So here's an example of using that. Here's tick at the top, and what we're going to do is do my sum, and this is going to be running over I from 1 to 100, and this is going to take the sum of these and print that out to the screen. So here's the end of that running down here. You can see that on the command window that we're getting up to 100 here, and then it hits end, right, as it completes the for loop. And then what will happen is it will report out the elapsed time in seconds. So this is able to count up to 100 in less than 1 second. We can use this to demonstrate the efficiency of the code. So what we can do is we can, for example, do 2 different ways of iterating. So here is an example of running with no pre-allocation. And here is an example of where we do a similar process using the pre-allocation here. So you see that here we're setting up the vector here, and whereas this one is causing the vector to expand each time we go through the loop. So here we go. When we run this out, what we can see is that this one takes 0.005 seconds, whereas if we did the pre-allocation, we can do that in 0.0002 seconds, which is approximately half the time. So then what we talked about today is we talked about iteration using for loops. We talked about regular for loops, and then we talked about nesting them and how that can be used to have 2 indices looping over things. We talked about while loops and their various uses, and we talked about loops with vectors and matrices, how they compare with vectorizing and how that can improve our timing, which brought us to our final topic of running tick and talk, which are going to complete the timing of processes. All right, so that actually brings us to the end of our lectures for this semester. Hopefully this has been helpful to you to learn some new material for your project and learning about MATLAB, and we will be talking soon about your projects. Thank you very much.
Professor Thayer. Professor Thayer.